All right, this assignment takes a subject we discussed before, which is a tank with water coming in. Now we're going to apply what we know about P-only controllers, proportion-only controllers, to control the level of the tank. So I like always highlighting the objectives. So I think of how so I always have a to-do list. That's something my mind needs. So we're going to develop a controller that can maintain a certain water level by automatically adjusting the inlet flow rate. And if you think about a control system, we always have a control variable, we always have a manipulated variable, and then we always have a our actuator here is the valve, but that valve controls the inlet flow rate. And what we're actually setting is the set point. So if we, really quick here, we've got a couple different examples for so here's our diagram. Let's discuss the diagram, let's discuss the fundamental equations, and then let's discuss our system. So we have an LT here, which stands for level transmitter. We also have an LC, which stands for level controller. The first letter in general will refer to what is being either measured or transmitted or controlled, and then the last letter will be what is happening to that. So here L is for level, C is for control, or T is for transmitter. TT is like a temperature transmitter, for example. AT is and CT. So AT is analyzer transmitter, CT is concentration transmitter. So that last T is generally transmitter. The second letter C is usually controller. So we have some balance for the change in height, which is dependent on this CU. C is some coefficient for the valve. So we're going to assume that it's 50, which means 50 kilograms per second per percent open. And U is going to be the valve setting. In reality, usually valves are not this linear setting. Some are, and that's actually a good advantage for some, especially in controllers, to have that linear setting. Others aren't quite that linear, and we'll discuss that later in the course. But two things to consider. One other thing to consider is that we can only limit open from 0 to 100%. We can't negatively open the valve, and we can't open to 150%. So we'll need to take that into consideration. Another thing to consider when we look at this system is that we're looking at the change in height over time. And what we want to do is actually look at the height itself. So we'll have to simulate this system, look at how we simulate the system, and look at how we control based on that simulation. What it will really come down to is that our change in height, let me get out my pen, our change in height over time will be equal to Cu over rho A. This is the amount coming in, and this is that rho and A accounts for the area and the density, since this is a mass balance. So that converts the mass to a volume, and then the area takes the volume and converts it to a height. If we think about it generally, a chemical engineering equation, we have accumulation equals in minus out plus generation minus consumption. Well, in some tank, right now it's a perfect tank, so there's nothing coming out. We're not generating water, and we're not consuming water. So the only thing that's accumulating is in. So that's our balance right here. Accumulation over time would be this dH dt, and height would be equal to the integral of dH dt over time, the integral over time. So let's go ahead now. Let's look at how we'll simulate this, and then let's look at our P-only controller. So we have a couple constants here, which we'll first plug in pretty soon. The first thing we'll want to do is set our simulation span. So we're only going to simulate for 10 seconds, with each discrete time interval being 1/10 of a second. So we're going to do that with this linspace function you've seen before. We have valve operation coefficients, so we're setting our C equal to 50, which again is units of kilograms per second per percentage open. And our zeros is going to be the same shape as our lens space. So we're going to have 101 rows, 1 column. And it's going to be set initially to zeros, and then as we manipulate our controller, each one of those rows is going to represent a discrete time point, and we're going to change that value at that specific element to reflect what we're interested in doing. Then we have an initial condition, an initial valve position as well. Then for storing the results, we have Z, ES, and SPS. So let's discuss what those are going to do in a moment. We'll also consider what is the value for U bias, what is the tuning value for KC, and then we'll record the desired level, so the set point. So we'll set the set point to 10. We'll say that we'll decide on a KC. So KC is a tuning constant that relates the percentage, it relates error to the setting U. So let's go ahead, let's look at our simulator with ODE int, and then let's maybe come back to some of these questions. Actually, so let's do this. Z, ES, and SPS. Whenever we evaluate, we need to evaluate relative to some error. So we need to first know the height at a given time. We need to know the set point at a certain time. We need to know the error, which is the difference between the two. You can think of this as the process variable, the set point, and then the error between the two. So we have this S just to know it's simulated. So we have these three things to restore, not results, but necessarily states at different points in time. U bias here is going to be 0 because our initial value is 0. The point of that U bias is that when we turn on the controller, we wouldn't see some sort of jerk because of the controller turning on. So that U bias helps us kind of smoothly transition onto control. We also have a KC. I've just randomly selected 50. We'll discuss afterward how we would tune that KC value. Another way we could tune it is based on our tuning constants. If we open up really quick, we're on at lesson 11, so I'll open up lesson 11's lesson. Here we'll have the lesson video. You can say KC is equal to some constant with KP, tau p, and theta p. So if we were to simulate our model with a first order plus dead time model, as far as the filling up of the tank, we could come up with some relationship for KC depending on those FOPDT constants. Unfortunately, this is an integrating process, and so that doesn't quite work as well because the level would just keep on rising consistently. So we'll set KC equal to 50. What that means is for every percentage of error, we will open the valve 50%. Now that seems a little bit high in my opinion actually, so we're going to set it equal to 10. I don't like that. I like the aggressiveness of 50 because what we'll do is we will, let's do something like 20. The whole point is that as we get closer though, the valve will start shutting off. Finally, we want to record the desired level. So we'll set that equal to 10. These are in meters because our area is in meters. So if we take cubic meters, which is what we get when we divide by the density, and we divide out the area, then we'll get a height of meters. So now we get an error, which is the set point minus level 0. Level 0 is our initial level. Then as we loop through, we need to set what the valve setting will be equal to. This is where we're going to program the P-only controller. The P-only controller setting will be equal to KC times error. And that's it. That's our P-only controller. Then we need to clip the limit between 0 and 100. And so we say the maximum it can be is 0 or valve. That will get rid of negative values. And we say the minimum it can be is 100 or valve. And that will get rid of negative values, values over 100, not negative values, is what we just did. Finally, we will store our results. We'll restore the valve setting in our U array, which stores our manipulated variable. We'll store our error. We'll simulate 1/10 of a second with ODE 45. And then we will take the last point of that simulation and we'll store that as our new level 0. And then we'll store that level 0 within our z, which is the height. And I just did z so that we don't mix it up with other variables. Finally, we set our set point at the next time as our set point. Right here. We could also change the whole array, make a whole array of set points, and that's what we'll do later in the course. Finally, we'll do a subplot with 3 different plots. We'll have one for the level, one for the valve setting, and one for the error over time. So let's go ahead, let's run our simulator and see how we do. So we have tank level, so we're at 0 initially, and we slowly approach it until eventually we do. And I should say eventually we do. We never quite will, because it'll always be slowly turning off as we get closer and closer and closer. But you can see it's effectively there. We're approaching it. So you see our valve shoots up to 100% and then slowly turns off as we get closer and closer. So there you have it. This is P-only control. Here is the level for the function for the tank level, by the way. I forgot to mention that. We don't depend on integrating values for the change in height of the tank, and we don't depend on the height of the tank does not depend on time, and it does not depend on the height of the tank. The change in level of the height of the tank, so the derivative of height, does not depend on height itself. It only depends on the quantity coming in, which depends on C in the valve setting. So there you go. I'll state that one more time to make sure I'm clear. The derivative of height of the tank does not depend on height or on time, and so that's why we have these 2 tildes, to explicitly say we need this spot saved for the way ODE 45 works, but we do not need those arguments. Alright, there you have it. Let me know if you have any questions. Thanks for watching.